So we've been talking about apertures or openings that were slits. So we have a slit, light goes through it. So we have a slit, light goes through it, and images onto a screen. But what if that aperture, instead of being a slit, what if the aperture were a circular opening? Well, that makes it more complicated because part of it is wide and part of it is narrow as light goes through. And so this makes it look this means that we cannot just say that the light from one side interferes with light from the other side as much because there's less sides here. Now remember, the narrower the aperture, the more the light spreads out. So it doesn't spread out as much around when the light goes to the mid part as it does when it goes to the ends. Well, actually calculating this involves some two-dimensional integrals, so we're not going to really worry about doing the calculation. We're kind of short on time, last set of lectures here, so I'll just give you the answer. And the answer here is that the resolution the resolution here, sine of the angle, is going to be 1.22 lambda over A, where A is the diameter. The 1.22 comes from the integrals. Well, if you're looking at something really far away, so you're looking at something really far away here, this is going to be a small angle. Sine theta is approximately tangent theta for small angles. Tangent theta, if we call that distance y and the distance x there, this is going to be y over x. So we can rewrite our previous equation, y over x, that's the sine or tangent theta, equals 1.22 lambda over a. So we can do an example of this. We can say, for example, that it's nighttime and you're driving down the road. And so you're driving down the road here at night, and there's a car coming at you, and we have two headlights. And so let's say the headlights are a separation away from each other. So that's the two headlights are a distance of let's say they are going to be 6.1 feet away from each other. And I want to know, at what distance do you actually see two headlights? Well, your eye, circular apertures. So let's say at nighttime you're partially dark adapted, but not totally dark adapted because all the other lights are hitting your eye. So let's say your aperture of your eye is going to be 3.5 millimeters. So I want to know, assuming middle of the visual spectrum, 500 nanometers wavelength, what's distance do you start to see two headlights instead of just a bright light in the distance? And so, well, we just figured this out. Y over x, 1.22 lambda over a. So x is going to be that distance right there. So that's going to be equal to YA over 1.22 lambda. So y, 6.1 feet. Okay, 3.5 times 10 to the minus 3 meters, 1.22, and this will be lambda 500 nanometers, 10 to the minus 9 meters. Okay, and so the x, if you multiply that out, and again, we don't have to worry about feet and meters because the meters cancel here and leaves behind feet. So if you multiply all this out, what you get is 350,000 feet. Okay. So what does that mean? Well, 350,000 feet turns out to be a distance of 66 miles. So if it's farther away than that, you would not be able to see that you have two separate things right here. So that's one example. I have another example. This time of year, you get out in the mornings and you look up and you can see the planet Saturn. Now, Saturn is a planet with rings around it. And so you wonder, well, why do you not see the rings around Saturn? Well, again, let's say that you're dark adapted. So your vision at night, your pupils are going to be fully dilated. So let's say that the aperture is now 5 millimeters. Okay, so that's actually extremely dilated. Okay, so what would that mean? Well, that means that if you look up Saturn right now, the distance to Saturn, x, is going to be 1.474 times 10 to the 12 meters. The rings, if you look at the rings from one side to the other here, y equals 2.6 times 10 to the 8th meters. Okay, y for the planet, if you just, that's the rings, for the planet, then that's 1.205 times 10 to the 8th meters. Okay, so what's the smallest that you could see? Okay, smallest thing that you could see is y over x, 1.22 lambda over a. Okay, so the smallest you'd see is 1.22 lambda x over a. So 1.22 times 500 nanometers times the distance, 1.474 times 10 to the 12 meters, divided by aperture, 5 millimeters, so 0.005 meters. And so the smallest thing that you'd be able to see in this sort of environment is about 1.8 times 10 to the 8 meters. Well, that means you could technically, that means you couldn't see that separate. I mean, that means the planet is actually a smaller feature than the rings. And the rings aren't all that bright, but you're still seeing the light of the planet smeared out over the rings. And this, of course, this assumes that you've got very well dark adapted eyes. So what if your eyes are not that well dark adapted? Then what happens? Well, if you assume that instead you have 3 millimeters, so we would change this down here to 0.003 meters. And so what would happen is that this entire thing changes. So you're still somewhat dark adapted, but not supremely dark adapted. Now this comes out to be 3 times 10 to the 8 meters. Now, that's actually bigger than the rings themselves. So does that mean you don't see Saturn? No, of course you see Saturn. It just looks like a dot. And in fact, what happens is it's just still going to, the light is going to spread out going through your eye. So you're going to see, it doesn't matter what size it is. Any size from this size smaller is going to look exactly identical to you. And so that's what this resolution is doing. It's not meaning you can't see anything smaller than that. It means you can't resolve or differentiate anything smaller than that. And so here we have it. You know, if you got really, really well dark adapted eyes, you're going to actually see better resolution than if your eyes are only somewhat dark adapted. If they're not at all dark adapted, you don't even see that well. Again, this an example of this sort of thing is if you have cats. Anyone that has a cat, drag a string in front of the cat, and their eyes dilate. Their eyes dilate, and that actually gives them sharper vision. They're carnivores. They're hunters, and so this is an adaptation that allows them to hunt better.